We present AdaptNet, a novel approach to quickly adapt a pre-trained policy for physically based character control to new tasks under the framework of reinforcement learning. AdaptNet consists of a latent space injection component that modifies a pre-trained policy by editing the latent space and an optional control refinement component that further fine-tunes the policy. Using our approach, a pre-trained policy is used as a starting point to quickly and efficiently produce skilled motion behaviors for a variety of new settings and tasks. This includes motion stylization, interpolation between styles, and morphological and environment adaptation. Motion stylization is easily achieved using AdaptNet and a few-shot type learning process that adapts the pre-trained policy to perform the same task, but representing the style of the target motion clip. Here we see a walking policy retargeted to different styles, such as joyful walking, stooping, and limping. And again, showing a running motion retargeted to the same styles. Motion stylization is achieved in less than 30 minutes. Here, we demonstrate the ability of our method to produce policies that smoothly interpolate between an existing pre-trained policy and a stylized policy. We interpolate in the latent space provided by the pre-trained policy by controlling the injection level of AdaptNet. Through adjusting a scale weight parameter, we can control how much stylization is added. Our approach also allows policies to be efficiently adapted to different character morphologies and dynamics, which cause the original controller to fail. Here we show the success of policies retrained using AdaptNet for body shape variants with different limb lengths and masses. Here, we demonstrate the effectiveness of the AdaptNet approach for improving the robustness of walking and running controllers. The pre-trained controller can handle small perturbations, but the character will still fail when there is a sufficiently large perturbation. The AdaptNet agents are trained by randomly applying impulses in different directions on the character's torso. This training step requires only a few hours. Yet the new policy allows the character to stay balanced even when 1,000 newtons of force are applied. Here we also show the effectiveness of AdaptNet when certain joints in the character skeleton are removed. This changes the dynamics of the character model, and hence the pre-trained policy often fails to maintain balance. Using AdaptNet, the updated policy is able to perform the same locomotion tasks and maintain a similar level of responsiveness to that observed in the original controller. AdaptNet may also be used to fine-tune control policies for changes in the environment. Here, the friction coefficient is drastically reduced compared to the original training environment. The updated policy is able to maintain balance by allowing strategies where the character learns to slide its feet and lower its center of mass slightly. Want your characters to walk over rough and uneven terrain? No problem. Using AdaptNet, our approach allows the state space to be extended to include local terrain height map information, which is then encoded by an extra conditional encoder to adjust the behavior of pre-trained policies. In this case, the encoding module is a convolutional neural network. By introducing a height map as the additional control input, the character is able to traverse and navigate a number of extremely challenging terrains where the pre-trained policy fails. Starting from a pre-trained policy without collision avoidance, the agent can be adapted to perform local planning and obstacle avoidance successfully. In the following, we compare the performance when different target latent spaces and internal adapters are employed. The injection at space 0 and the employment of full-rank adapters lead to better motions. We refer to the paper for more technical details and discussion. Here we show the performance when different regularization is applied to the injected latents. Regularization is not always necessary. For example, in this stooping style transfer task. However, there will be a risk of overfitting when no regularization is applied, while a large value of regularization will make AdaptNet fail to learn stylized motions. Thanks for watching.